you, if you don't have a calculator, then you can just see what we're doing. So this is what you will need to reference when you're working on the homework, which I'll talk about at the end of class. So let me go ahead and switch over to my iPad. And yes, Jada, I am recording. So thanks for reminding me, everybody. I always need somebody every single class to remind me to hit record. There we go. Okay, so questions 6 and 7 on the bottom are talking about wavelength and mass. So the whole notion of de Broglie's thing with wavelength is he said electrons are not, they're not actually particles, they're waves, which is kind of weird, but he was like, okay, so if they're waves, you know what? Every particle is a wave. It's just that some waves are so big you can't notice them, or they're so small that it doesn't really matter, or things like this. So it's a weird notion. It doesn't really particularly matter, but I did want to point out that this is 6 and 7 are when we use this equation. Okay. So that is for questions number 6 and number 7. So its wavelength is equal to h, that's Planck's constant again, divided by the mass in kilograms times the velocity or the speed in meters per second. And that will spit out a wavelength in meters for us. So that's what we're going to use. So let's go back and see how that applies here. So question 6 says, an electron moves with a velocity of 2.5 times 10 to the 8th centimeters per second. So that is the V of that formula. What is its wavelength? So it's asking for that lambda thing. And it says the mass of an electron is 9.109 times 10 to the negative 28th grams. So here's the only thing. I have all the pieces I need, right? This is my formula. H over M times V. H is a constant. I have the M and the V, but the mass needs to be in kilograms and the velocity needs to be in meters per second. So I have to switch these things. Okay, so if I am moving from centimeters to meters, which direction am I moving my decimal and how many places? Centimeters to meters.
2 places to the left.
2 places to the left. Okay, so I'm moving 2 places to the left. So if I'm moving this 2 places to the left, that velocity is 2.5 times 10 to the what then?
Negative second.
Well, it was times 10 to the 8th.
6th.
So it should be times 10 to the 6th. Okay, so I've now got 2.5 times 10 to the 6th meters per second because I chopped 2 off by moving it 2 to the left. Does that make sense?
Yep.
Okay, so I need to kind of do the same thing with this mass. This mass is in grams and I need it in kilograms. So from grams to kilograms, I'm moving how many places in which direction?
3 places to the left.
3 places to the left. Now, this one is negative. the first one was positive. So 8 going to 6 was making that exponent smaller. So I need to make this negative 28 3 places smaller. So what does it become if it's 3 places smaller?
Negative 31.
Negative 31. Okay, so now I have a mass, I have a velocity, and this is a constant. So I can plug them all in and see what I've got. So my wavelength, that constant, Planck's constant, 6.626, 10 to the negative 34th joule second, over, you've got 2 things in the denominator here, so your brain should automatically go, you know what, I want parentheses down there so that mathematically this works out the way I want it to. So I'm gonna open a parentheses and put my 9.109 times 10 to the negative 31st kilograms times my velocity, 2.5 times 10 to the 6 meters per second, and put all that in there. And if I look, I've got a 10 to the negative 31st and a 10 to the 6th. So that's about a negative 25. And a negative 34 divided by a negative 25, that cancels out to leaving me over about a negative 10, negative 11, something like that. So if you plop all of this into your calculator, how many sig figs are you going to end up with?
2.
2.
2. You've got 1, 2 right there, so you're going to have 2. So if you have, if you enter in 6.626 EE negative 34 divided by, open a parentheses, 9.109 EE negative 31 times 2.5 EE 6 close parentheses equals, you should get 2.9 times 10 to the negative 10th meters. That is a really small wavelength, and it's not a wavelength that anything you would actually be able to see, but that would be the wavelength of an electron. There it is, the wavelength of an electron. In terms of all of those units canceling out, I don't want to get into how it cancels out, but what you need to understand is that a joule is actually a combination of kilograms and meters and a bunch of other things. So just trust me in that all the units cancel out in this formula and it's done correctly, because I don't want to jump to physics and go through that, because I don't fully remember what the hell is in a joule anymore, because I don't need to. So number 7, we're going to do the same thing, right? Calculate the wavelength associated with this mass of a golf ball moving at 30 meters per second. Okay, so wavelength equals Planck's constant times mass times velocity. My mass is in grams. I need it to go into kilograms. So that is, again, 3 places left. So if I'm making that 3 places left, well, let's see here. That's actually 100. So 3 places left, that's going to be 0.1 kilograms. So that's about the mass of a golf ball, right? You know, it's kind of small. My velocity needs to be in meters per second. It's already in meters per second. So that's good. So 6.626 times 10 to the negative 34 over, open a parentheses, 0.1 times 30. What are you going to expect on your exponent in scientific notation on this guy looking at what's in the denominator? Is it going to be big or small?
Big?
Small.
It's
Small.
going to be small. I've got times 10 to the negative 34 in the numerator, and I hardly have anything in the denominator to cancel it out. So my sig figs here, if I'm paying attention, my sig figs here, because I've got a decimal behind that 30 and a 1.0 here, how many sig figs am I going to have?
2.
2 again. So for 2 sig figs, if I do all of this, I'll end up with 2.2 times 10 to the negative 34th meters. That is exceptionally small. That is the wavelength of a golf ball when you smack it. You could not see that. Just like the wavelength of a baseball when it's coming off the bat is so small that you can't see it actually like go traveling in a wave. It does, but it's not visible to the human eye. It's probably not even visible to a camera. You wouldn't be able to like slow-mo be able to record that thing. But mathematically, it is traveling through that wavelength. Now, that's in meters. If I threw it in nanometers, going from meters to nanometers is how many spaces?
6.
9.
Nano, 9. Nano is 9. So if I'm moving it 9 spaces that way, that negative 34 gets 9 spaces bigger. So it would be 2.2 times 10 to the negative 25th nanometers, which is still really, really tiny. And then this last question, I don't care about the last question because I think all I ever am asking you to do is wavelength. So, but if I wanted to take the time with the last question, it wants to know how fast a ball must travel to do this. So if that's my formula, and I want to know how fast means I'm looking for velocity. So rearranging this formula for velocity gives me that. So, and if you wanted to do that and see if you get the right answer, I will tell you the correct answer there is 1.2 times 10 to the negative 21st meters per second. So you can do that on your own. So let's turn this baby over. So on the back of this sheet, actually all of this was, my bad. Make sure you're on the right tool. Okay. All of this is from section 5.1. So I'm not going to go through that. If you wanted to double check yourself that you still remember how to do this, I'll tell you the answers there are 90.50%, 9.50%. That's the answer for part 1. For part 2, the answer would be 3.557 times 10 to the 22nd atoms. But again, that's old material, so that's not what we're going to focus on. So I want to look at parts B and C because that's the relevant information, for what we're doing right now. Okay, so B says a major line in the emission spectrum of neon corresponds to a frequency of this. Calculate the wavelength in nanometers of light that corresponds to that light. So if you look on the other side, which of my formulas do I need to calculate wavelength if I have frequency?
New.
All right, I'm using nu. So frequency is nu. And this one is lambda. So what is that formula?
Lambda equals C over nu.
Uh-huh. Okay. So C is what?
2.998 times 10 to the 8th.
That's the speed of light. It is a constant. It's on the front side. It's not going to change. And then my frequency, they've given it to me in the correct unit. So all I have to do is plug it in. Inverse seconds. So if I plug those in, again, you should think about your answer logically. I've got 10 to the 8th in the numerator. I've got 10 to the 14th in the denominator. So that should end up with something about the negatives around -6, because 8 minus 14. How many sig figs should I have?
3.
3, based off of that. So if I do this to 3 sig figs and plug this in, I get 6.91 times 10 to the -7, and that's in meters. But they want it in nanometers. So again, meters to nanometers is moving 9 spaces to the right. So 9 spaces bigger. All right, so that is going up 9. So that is going to give me 6.91 times 10 to the 2nd nanometers, which is 691 nanometers. Either one of those would be correct. William, are those Bentleys or Rolls Royces in the background?
Those are Rolls Royces.
Rolls Royces, nice, nice. Okay. So this last one. Says in the upper atmosphere, ozone decomposes, blah, blah, blah. So here's our little equation. Great. A molecule of O3 absorbs a photon with a frequency of this. So I've got a frequency. It says how much energy in joules does it absorb per photon? Okay, so I've got energy and frequency. What's my formula?
E equals H nu.
E equals H nu. H is a constant, 6.626 times 10 to the -34th joules seconds. Frequency is right there. It's real easy. S to the -1. Do you even need a calculator to do that? You're multiplying Planck's constant by 1. So I would hope not. 6.6, I'm not going to say 26 because I only have 3 sig figs. I'm going to say 6.63. But if I was doing this mentally, -34 and +15, what is that going to give me? Times 10 to the what?
-19.
Yeah, -19. So the other thing to remember is that all of your joules are going to be around this, right? For what we are doing, all of our energy values are around times 10 to the -19. That is a good mental check to know you set up the problem correctly. So that's how much energy we're talking about. Then the second part of the problem says, well, the minimum amount of energy needed to break an oxygen bond in ozone is 387 kilojoules per mole. Does that photon have enough energy to break this bond? Well, you have 2 different ways to do it. You can either see how much individual stuff is in the 387, or we can convert this guy. I'm going to convert this guy. So if I had 6.63 times 10 to the -19 joules, I need it to be in kilojoules. So there's 1,000 joules in 1 kilojoule, but I also need it to be per mole. So I need 1 mole in the denominator. So what number am I going to stick in the numerator here if I'm talking about 1 mole? We did it on the front side in one problem.
Avogadro's.
Avogadro's number 6.022 times 10 to the 23rd, because this number is for a single photon. All right. And I want to know if I had a mole of photons, right? Not a single one. So now I'm going to take 6.63 times 10 to the negative 19. I'm going to knock 3 things off by dividing it by 1,000, but then I'm going to have this times 10 to the 23. So I'm going to multiply all of that stuff out into 3 sig figs. That's going to give me 399 kilojoules per mole. So that's what I get from that photon. Is that enough energy to break that bond? I'm comparing the 399 to the 387. Can I break the bond?
Yes.
Yes. So this is how much is produced, right? This is how much is needed. How much I produced is bigger than what's needed, so I will break the bond. This is actually the entire point of ozone in the atmosphere, is to do literally this thing and absorb this this frequency of light as a protective layer. So there you go. Okay. So that's the calculation. So if I remember correctly, I can correlate, I think, every single homework problem that's on 5.2 is 5.2, 5.3 is on here in one way or another. So I can send out a message later that kind of tells you which one to be looking at to be able to do all of that. Let me switch back. Yeah, I'm hearing you guys about the audio. I'm not sure exactly what's going on. Hopefully my video recording is not problematic, so you can go back and watch it. But if so, you guys can just let me know, and I can do another straight recording later on of all these calculations and send it back out if that's a problem.
Thanks.
Okay, so we've all been talking about Bohr, and what I said in the Edpuzzle video that you guys did for this week is Bohr was wrong because Bohr's model only worked for hydrogen. As soon as you started having more electrons, his model kind of fell apart and it didn't predict things correctly. So clearly Bohr was not correct. De Broglie comes along at about the same time and is like, yeah, so I think instead of being particles, like Bohr says, I think electrons are actually waves. And I think that's going to be able to explain things. So he basically just said the exact same thing Bohr did, but as waves. And guess what? His model failed for everything but hydrogen as well. So that's certainly not correct. So he's missing that as well. And then there's this guy, Schrödinger. Schrödinger, if you've ever heard about Schrödinger's cat, it's a thought experiment. This is the Schrödinger of Schrödinger's cat. And he said, well, actually, it's not that electrons are particles or waves. They are both at the same time, which is kind of weird, but that's what we're getting into, and that quantum mechanics is a little weird. And this other German guy, Heisenberg, said, well, you know what? We can't actually know what an electron is because they're so small and they're so fast. So all we can ever do is just make a guess. And this is accepted scientific theory to say, we're just going to make a guess. So the guess we are going to make is based on this last model that I'm going to pull back up. And this guy actually does a pretty decent job of it. Okay, so this right now is what Bohr says is going on, right? So we shine a light, the electron jumps up, falls back down, it's giving off things, blah, 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 right? But we see our nice little, neat little circles. We've got orbits, and if you watch that electron, it is traveling in a circle around the nucleus the way a planet circles the sun. And this made sense to them at the time because astronomy made sense. The difference is planets are giant objects. Electrons are tiny. You can mathematically predict where a planet will be years from now, but you can't do that with an electron. So that's part of the reason why Bohr's model fell down. So, but this makes sense to us. And when we conceptualize what is happening in an atom, our mind jumps to Bohr's model here because it looks like it should make sense. So sorry, it does not. So when we talk about de Broglie saying this thing is a wave, this is what we mean. It's like a rubber band in a little ring. And then when it gets hit with light, it's that the rubber band stretches and gets bigger, but it looks like basically like a harmonic wave. And so much so that I love pulling this thing to this side so you can see, so you can really kind of see its waves there. But it should make sense that if an electron is a wave and it has a very specific wavelength, you can only add a full wavelength and it's going to give you those various sizes. So de Broglie could explain like the sizes of energy levels a little bit better, but we all know that an electron is not a rubber band. It's not a stringy big thing, like it's dumb. It doesn't make sense. So de Broglie doesn't make sense either. And instead what we get is this weird thing. There is no electron there. See that little blue shading of stuff? That's where we think an electron could be. And that's all we can know. So before I hit play, I want to point out, if you look at the energy levels diagram over here, it's different from the others. See, Bohr's, you had 1, 2, 3, 4, 5, 6. That is literally what I recreated on my dry erase board. But you look here, it's not just 1, 2, 3, 4, 5, 6. Why is it going off here to the right? What are all of these things? That's new. So the electron here is not a distinct thing. And in fact, when you get excited electrons, you end up with these fuzzy little shapes. And it's because these are what we refer to as electron clouds. Oh, it's still cutting out. Yeah, damn it. So you get these fuzzy clouds, these fuzzy little shapes of electrons. And this is what basically quantum mechanics explains. Like, this is what is actually happening in an atom. So we can mathematically calculate this. We can do all of these experiments that prove that this is what, what's happening, and that's fine. So it's a little bit harder to visualize, but this is what's going on. So I want to, whoops, not what I meant to do. Okay, anyway. So this is what we're going to spend several days going over. Quantum mechanics, quantum theory. So the whole important thing here for you to know is that electrons, they are, and if there's any parents in your room right now, turn your audio off. Electrons are not planets that orbit. Electrons are magical motherfuckers. That's what we say. We call them magical motherfuckers because they move magically. These are like the Harry Potters and the Captain Kirks of the universe. They apparate and disapparate at, you know, their own will. They are like little transporter beams going in and around. The electron does not travel in a path. It does not move from point A to point B. What the electron does is it disappears at point A and simultaneously reappears at point B. Hence our notion of magical motherfuckers, because nothing else does that in the world. But that does mean that in theory, the whole notion of transporter beam technology from Star Trek is actually possible. And they've done it with very, very small things. So what quantum mechanics is going to say is that electrons behave as both a wave and a particle at the same time. But it is impossible to know how fast it's going and where it is at the same time. Because if I try and see where an electron is, the act of seeing it will change its speed. And if I try and measure how fast it's going, the ability to measure how fast it's going will actually change its location, because it's so small that anything you do is going to affect it. So we can't actually know where these things are, which means that what we do is we calculate their probability, and we call these electron clouds, they're probability clouds. They're actually mathematical distributions. They're not actually like clouds, like fluffy things that we think of as clouds filled with water droplets. We're using the cloud in its mathematical term. So it's a probability distribution of where we can find these things. And to be able to calculate these like crazy statistical models, Schrodinger used something called a wave equation. I did not even have to know how to solve a wave equation through all of my years of chemistry. To actually write one wave equation out would take a full piece of paper for one equation. And it uses it uses differential equations and linear algebra, which is above calculus. So that is not a thing we will do. But there's 4 variables at play in those wave equations. So we are going to actually drill on next class on what those 4 individual things are. But basically, you can define where you should be able to find an electron. So what we are going to focus on, come on now my internet, there we go, is what we're going to say is that you can find electrons in orbitals. Those orbitals are inside sublevels, and those sublevels are inside energy levels. This is where we're going to pick up on Thursday. So what I am going to teach you to do over the next week and a half is to basically write the address of an electron. So just like you have an address that writes down your house number, right, your city, your state, all that sort of stuff, and it identifies where you are, we can write an address for an electron that allows us to say where we should be able to find an electron most of the time. And it's going to be an energy level, a sublevel, and an orbital. So that's what all of that weird code that's written in section 5.4, that's what it's all talking about, is its location. So that's where we're going on Thursday. So for Thursday, in theory, 5.2 and 5.3 homework is due on Thursday. However, I'm going to count it for 4th term and not 3rd term. So you take that for what you will, but I do have a link ready for you to submit your answers in the Google form, and to send the scans as always. I will send out a remind message later telling you which problems to look at on the calculation practice that correlate to the homework questions, so you can see the examples of how to do that. And then I do have office hours and stuff where you can ask questions or send me pictures and stuff for this week. So for Thursday and next week, as we're dealing with this electron arrangement, you should have 2 packets behind section 5.4 that we're going to work from, and we're going to consider these notes. One is titled The Mighty Packet of Electron Arrangement, and it's stapled together. It's a couple pages stapled together. That's what we're going to start with on Thursday. And then there's another one called Advanced Electron Arrangement Topics. These are the two things that we are going to use as notes to figure out what electrons are doing. That's how I'm going to break down section 5.4. So look and find these things. If you don't have these things, you either need to use the link at the bottom of the weekly plan that has all of the documents on it to be able to find it, or just send me an email and say, yeah, I'm going to need those again, because you're going to be real lost next class. If you're trying to do this on notebook paper, you want those packets. Okay, Friday is Records Day, so office hours on Friday are canceled. I will be posting a new Edpuzzle video today that will count for term 4. The 5.2, 5.3 homework will count for term 4. We are squarely now in section 5.4, so if you haven't looked at that, you should look at that. Otherwise, between now and Friday is just try and get everything tidied up for term 3. And like I said, the instant I know more information about what term 4 is going to look like, or what we're going to do, or literally anything about it at all, I will let you know. So otherwise, I need you to sign up for the Google Classroom if you haven't yet. So make sure you're signed up for that by next week, because I'll start transitioning over to that. And fill out that course recommendation survey for me, which I will send out again. Okay, questions and or goodbye if you don't have any.
Okay, wait, hold up. Before everyone leaves, can we sing a very special someone a happy birthday?
Who?
This is for you, Allison.
Oh my God.
Oh, it's Allison's birthday. Okay, I'm really bad at this, so somebody else should lead. Moya, you started it. You go ahead and lead.
It's going to be delayed.
That's okay.
Okay.
All right,
Why don't
let's
we
go.
just get Mr. Bose to sing it?
Happy birthday to
Day to you.
Happy birthday to
Where's all my vocalists? Come on.
Where are you?
Happy birthday, dear.
Dear Allison.
Happy birthday to you.
Woohoo! Oh my God.
Oh,
You should ask me at Metro PCS. Miss Baskin, I have a question.
Yes, Alyssa.
What's the regular science that 11th graders take?
I mean, you can choose, but
Oh, you choose. So you don't have to take anatomy?
you don't have to. No, most
Okay.
juniors do, but you don't have to.
Okay.
Girl, you're taking my class. What are you talking about?
I know. I'm taking 2. I'm going to do physics too.
Oh, okay.
Okay, that's all I had.
Okay.
Bye, Miss
Yeah, next year is going to be a very vocal heavy. It's going to be a very vocal heavy AP class. I love it.
I should
Yeah,
be able
Happy
to
birthday, everybody.
Bye.
The smarter vocal classes.
Bye, y'all.
Bye.
Bye, Miss Baskin.
Bye.
I'm Justin.